Hi everyone, in this video we are going to discuss what happens when you take a strong acid and you treat it with a strong base. And so essentially what happens is a neutralization reaction. So you take this strong species and another strong species and they cancel each other out. So you're left over with a very, very boring neutral solution. So let's go through that in a little bit more detail. So let's start off with a very simple definition. So a neutralization reaction is the reaction that occurs when a strong acid and a strong base are mixed. So let me show you this from a very, very simple reaction. So every single neutralization reaction has to take some kind of acid component, so H+, remember this is your strong acid, and from here on out I'm going to label strong acids as SA, okay? Then we're going to treat it with OH-. So remember OH- indicates that we have a strong base, and so from here on out strong base is going to be SB. So now when we take H+ and we treat it with OH-, we create a species called HOH, which sometimes people like to refer to that as H2O, also known as water. And now water is neutral. It's neutral. It's not a strong acid. It's not a strong base. If we drink water, we know A, it doesn't taste sour, so it's not an acid, and B, it does not taste bitter, so it's not a base. It's considered neutral, all right? So this is the generic equation, generic version of the neutralization reaction. What I need you to be able to do is actually predict the products when we take strong acids and strong bases and put them together. So let's look at an example. So we have HCl, which we know is a strong acid, and we're going to treat that with sodium hydroxide, NaOH, which is a strong base. Remember, I asked you to memorize 3 of each. That's all you have to do. So now what we're going to do is try to come up with the products. What are we going to create? The easiest way to do this is start off by looking at your salt, or your cations and protons, your classic ones. So you see a Cl right here, and I see an Na right there. So what we're going to do is try to bring those together. So essentially a double replacement reaction, if you know what that is. So we're all going to swap partners, basically. And so these two then come together. Your sodium and chloride come together, and you form a salt. And then your other two species left over, you've got your H right here and your OH right there. We bring these two pieces together, and we create HOH, also known as water. And so every single time you bring a strong acid and a strong base together, every time you're going to create a salt and a water, every single time. So now you try one. What are going to be our products when we take, let's see here, let's use nitric acid, so HNO3, and we want to treat that with potassium hydroxide. What salt are you going to create? Go. All right, did you get an answer? Hopefully you did. If you didn't, that's okay though. The easiest way to do this is just try to eliminate water right away. If you see that you have a strong acid and a strong base, automatically you know I have to make water. So you know you're going to make an HOH compound. So then everything that's left over is going to make your salt. So your salt has to be your cation first, so that's your potassium, followed by your anion, or in this case your polyatomic anion. So you end up with KNO3, or potassium nitrate. This is your salt. That's what I was looking for. And then you definitely have to also create water. So now, anytime you have a neutralization reaction, people will say you take a strong acid, you treat it with a strong base, you get a salt and a water, but we can actually call this a neutral solution. So a neutral solution is just going to be when you've taken some solute, which in this case is our salt, KNO3, and you dissolve it in water. Neutral, not an acid, not a base. Well, this is a neutralization reaction, okay? Make sure that's very clear. So now, what's neat about this is in a neutral solution, we have very unique properties. Our H+ concentration, reminder, every time I use those brackets, I'm just saying concentration, and usually we're indicating a molarity concentration per unit, okay? Our H+ concentration is equal to our OH- concentration, and they are each equal to 1 × 10⁻⁷ molar, okay? Each one of those in a neutral solution each component is equal to 1 times 10 to the negative 7th molar. So a teeny, teeny, tiny concentration, a very small concentration. But what we can do with this is actually come up with a formula and use this formula to then predict what the concentration of something's going to be based on the concentration of the other one. So we can predict this based on the concentration of your hydroxide, or you can predict your hydroxide concentration based on your hydronium concentration. So let's look at that formula. It's just like what you would expect it to be. You take H plus, you multiply it times your concentration of OH minus, and this will always, always, always be equal to 1 times 10 to the negative 14th, okay? And usually that's in molar. And so that is your formula. This is your big formula, which is always going to be true for neutralization reactions. So based on that information, if I tell you that you have a solution and its hydroxide concentration is equal to 1 times 10 to the negative 4th molar, I want to know what is the concentration of your hydronium ion. Go. All right, did you get an answer? Hopefully you did. All you had to do was use this equation up here and then solve for your hydronium ion. So what I would have done here is just rewritten this H plus concentration, that's what we're solving for, times our concentration of our hydroxide ion. So that's 1 times 10 to the negative 4th molar, and we know that's going to be equal to 1 times 10 to the negative 14th. So now all you have to do is take 1 times 10 to the negative 14th, divide it by 1 times 10 to the negative 4th, and you end up with your hydronium concentration equal to 1 times 10 to the negative 10th molar. Easy peasy, right? Be very, very comfortable with this equation. Make sure you can solve for both the hydronium ion and the hydroxide ion. That's it. That's all I've got for you today. Take care of yourself. Have fun.